Welcome to Back to the Basics Business Technology Platform, Episode 1. In this episode, we will talk about the concept of a database. What is it? How do we store data? What is actually data at first to start with? And then, once we are done with Episode 1, you will be able to go to Episode 2, and so on and so forth, based on the little agenda you see here. Before we start explaining what SAP HANA Platform is, it might be good to come back to the very basics of data storage and retrieve. So what does Wikipedia say? Wikipedia says a database is an organized collection of data, generally stored and accessed electronically from a computer system. Where databases are more complex, they are often developed using formal design and modeling techniques. The Database Management System, DBMS, is the software that interacts with end users, applications, and the database itself to capture and analyze the data. The DBMS software additionally encompasses the core facilities provided to administer the database. The sum of total of the database, the DBMS, and the associated applications can be referred as a database system. We will see in this series of videos that this definition is not sufficient anymore. Across the time, a complex environment of technologies related to data has been developed. People rapidly understood that simply storing and retrieving data had to be complemented with tools allowing to safely, securely, and performantly operate the data by transferring, replicating, virtualizing, enriching, validating, tracing, and other activities. So, across the time, database systems have been replaced by database ecosystems. And that's exactly what SAP HANA is. A platform allowing to handle all aspects of your data management. What we will see in this series of videos is how SAP answers all these challenges. So, a database is an organized collection of data. This very broad definition will then cover all possible technologies, from simple text file, stored in a file system, to much more sophisticated software like relational database or NoSQL database. Before we point out the differences between these tools, it might be important to recognize that we do not produce data today the same way we were producing data 30 to 40 years ago. Because of the advances in technology, we can produce data in more sophisticated formats like streams, images, audio, or others. Today, data formats are commonly categorized in three main families: structured, semi-structured, and unstructured. Structured, we know in advance the type of the data, integer, character, etc., the length of the data, its position in the chain of bytes, often called a record, and how to interpret it from an end-user perspective, like name, email, address. All the records have the same layout. Very often, the preferred language tool to manage them is a relational database system. Semi-structured. It is a form of structured data that does not obey a formal structure like structured data, but nonetheless contains description called tags and other markers to separate semantic elements and enforce hierarchies of records and fields within the data. A typical example is the JavaScript notation, JSON, where all elements of data have a description of their meaning standing before the value itself. It is also known as self-describing structure. Now, unstructured, all information that either does not have a predefined data model or is not organized in a predefined manner. Typical examples are video, pictures, audio, text. To get value from these type of data, we need to use advanced technologies that will deduct information From this set of bytes, technologies like voice or face recognition, text analysis, or other will analyze the content of the data to create new descriptive information, often called meta tags. It is important here to understand the fundamental differences between data residing in a file system and data residing in an advanced tool like a relational database. If, on a file system, you can organize your data in folders, hierarchies, and files, it will be difficult to access the atomic data residing inside the file. It is even more challenging to maintain the data in their evolution, like updating or deleting. To do this, you will have to use additional external tools like text editor, Word, Excel, or other applications capable of accessing the content of the file. In a relational database, all data are organized into structured tables where the data are inserted, maintained, and queried through a unique interface, commonly the SQL language. The whole set of structured tables is called the model of the database. The relational database system is also providing capabilities to validate the consistency of the data, as well as the quality, the coherence, the security, and the description of the data sets. All things that are very difficult to achieve with a file system. In a relational database system, there are various ways to internally store the data. Today, it is not still possible to get rid of any disk subsystem to ensure sustainability of the information or persistency. Therefore, when executing read or write transactions on the disks, it has always been challenging to find the balance between performance of the data storage and performance of the data transaction. It must be clear that writing 1 megabyte in one operation is faster than writing 512 times 2 kilobytes, but most of the operations are concerning a very small amount of data in the range of 200 to 500 bytes. That is typically valid for OLTP world. Therefore, the most common approach was to interact with storage using I/O of a predefined size like 2, 4, 8, or 16 kilobytes. This is often referred as a disk page. As said, that was working very well for OLTP, but very rapidly analytical queries looking for bigger amount of data came into the play and forced the database systems to have a different strategy. Today, two popular internal architectures to store the data are proposed, vertically or horizontally. When applying the horizontal strategy, you try to store a maximum of records into one page, and you use that page to interact with the I/O subsystem. In the context of analytical data model, it is very common to have records containing a lot of information of their columns, so the record size might be very big. Nevertheless, the experience shows that a small subset of these columns was used in a query, meaning we were forced to read too much data, the whole record, in regard to the actual query. And then came the concept of verticalization. Each column of a table is stored in its own set of pages, and the server has only to read what is needed to execute the query, not the whole data set. As already mentioned, data are not always very well structured, because structuring the data requires efforts that may impact the performance. We have seen along the years the emergence of different types of database technologies, the so-called NoSQL database. NoSQL stands for not only SQL, meaning they use a different storage mechanism and a different way to access and retrieve the data. These technologies complement the capabilities of our database systems by providing internal engines that can process the data differently. Some examples are document databases that are specialized in retrieving data from unstructured texts or graphs database that are used to detect relationship between the data like understanding the relationships of individuals in a social network. Relational databases requires a predefined schema, while NoSQL database detects the schema when executing the query. Queries might be far more complex in a relational database, while NoSQL database has less capable interface, unlike SQL. NoSQL database tend to better distribute the workload over the pools of servers, while relational databases tend to increase the hardware power of its server. Today, it is a fact that the cost of RAM is lowering, even if still higher than the cost of a physical disk, with a ratio of 40:1 in favor of the physical disk. Meanwhile, the ratio of performance to access the data is of 1 to 650 in favor of the RAM. So it might be very interesting for the applications requiring high performance to pay the price of the RAM to store a maximum of data into the memory. There come the concept of the in-memory database that can really benefit from the power of the CPU, while disk-based databases are actually losing and wasting a lot of time waiting for the I/O subsystem to complete its actions. Today, in an in-memory database, physical disks are playing a secondary role, simply ensuring the data persistence. Non-volatile memory that retains data without applied power will probably change the paradigm of RAM and storage subsystems. Is SAP a database provider? The answer is very simple: yes. We can provide database technologies that altogether cover the set of capabilities we mentioned in this presentation. SAP HANA is an in-memory database, offering both vertical and horizontal data storage. It compresses the data to reduce the memory footprint and offers many NoSQL capabilities mentioned earlier. It is intended to serve in both OLTP and OLAP analytical environments. SAP IQ is a disk-based database, offering both vertical and horizontal data storage. Its scalability is in the range of dozens of petabytes. It compresses the data to reduce the disk storage footprint. It can easily interact with NoSQL technologies. SAP ASE is a disk-based engine with in-memory capabilities. It is mainly intended to OLTP applications requiring extremely high volume of transactions and reliability 24/7. SAP SQL Anywhere is a small footprint database engine dedicated to departmental or mobile applications. It has a self-administration capability and comes with sets of tools allowing to manage complex IoT databases. Now that we know all this, see you next time for episode 2 explaining the concepts of SAP HANA. Thank you.